Math and Music, and this lecture is on self-reference. I hope it's good. That's a little bit strange. What is self-reference? Well, we actually closed last lecture with an example. I welcomed myself on screen to play the Mozart table canon. Now, there are many different kinds of self-reference. There are sort of everyday, common types of self-reference. You can talk about yourself. You can talk about yourself maybe in the first or maybe in the third person. When you look in a mirror, that's a version of self-reference. If I were to write a research paper, I could say in the research paper, see Theorem 2, which happened earlier in the paper. Or I could reference earlier work that I myself had done. That's a form of self-reference. Now, it would be weird if in a paper I would cite that paper. Maybe in a 2006 paper that I wrote, I could cite Kung 2006. That's a hint of weirdnesses to come. There's self-reference in popular culture, in everyday life. We think of something like the chicken and the egg problem. That's which came first. That's a version of self-reference. If you ever see two mirrors that are parallel to each other and you look at them and you can see the light bouncing back and back, you can see reflection and reflections and reflections. That's a form of self-reference. Magritte, the famous Belgian painter, painted a picture, Treachery of Images, in which it says, "This is not a pipe." Of course, it is a picture of a pipe. The opening of this lecture, where we saw infinitely many copies of me watching myself, that's a form of self-reference. You see it in sci-fi movies, Back to the Future. Marty McFly, that's Michael J. Fox's character. He helps bring his own parents together so that they can produce himself. Matrix, Inception, people dreaming about themselves. You remember in Matrix, the Oracle says to Neo, "Don't worry about that vase." And then Neo turns and knocks over the vase. Would he still have broken it if the Oracle hadn't said anything? Even in literature, there are versions of self-reference. In Don Quixote, Cervantes' protagonist, he understands that he's being written about. The character in the book talks about the book itself. Italian writer Italo Calvino wrote a book called If on a Winter's Night a Traveler, in which a character sits down to read a book titled If on a Winter's Night a Traveler. Gabriel Garcia Marquez wrote 100 Years of Solitude, a wonderful book. And in the final scene, Aureliano II reads a book that prophesies his family's history, including his reading that very book, all before the apocalypse erases the town of Macondo. Now, self-reference in math and music are both important in their own ways. But my main point today is this. Self-reference creates beauty and a bit of strangeness in both mathematics and in music. And the self-reference in these two subjects seems similar. Now, like last lecture on transformations, this is really an analogy. This isn't math directly applying to music or explaining music in some way, but I think that these two things, self-reference in mathematics and music, are very similar. Now, I personally think that in your brain there are neurological connections, that somehow it's the same schema needed to understand both mathematical and musical self-reference. Note that I just got your neurons to process thoughts about themselves, another form of self-reference. Now, a lot of this is going to be was brought to the fore by Douglas Hofstadter in his book Gödel, Escher, Bach, An Eternal Golden Braid. I remember back in high school, I joined the paperback book club to get a copy of this book. You know, it's a 1980 masterpiece of fantastical nonfiction. It won the Pulitzer Prize that year in general nonfiction. This book elucidates the common connections among Bach's music, Escher's art, and Gödel's mathematics. And I know that Gödel's work is probably the least well-known of these three. It includes ingenious dialogue, sort of like Plato would have written, with hints of the mathematician Charles Dodson, who you probably know better as the author Lewis Carroll. I'd actually forgotten how brilliant these dialogues are. You know, in one dialogue, there's a story about creating a record player. Each record player that's created has a resonant frequency, and if you make a record with exactly that frequency, it will resonate, and the record player will resonate and destroy itself. Now, you could make a new record player to play that record, but that new record player would have its own resonant frequency, and there would be a record that would destroy it. really brilliant ways of explaining difficult material in wonderful ways. Now, on the surface, this book is about math, music, and art. Underneath, Hofstadter is really talking about deep concepts. He's talking about self-awareness. He's talking about cognition. Now, today, we're going to talk about different levels of self-reference. There's basic self-reference, things like, I am Dave. There's no strangeness, there's no loops, and there are lots of musical and mathematical examples. We could also have intermediate level self-reference. That's something like, this sentence is true. And now you can start to see infinite loops appearing. That sentence refers exactly to itself, which refers to itself and again and again. The mathematical examples of intermediate self-reference become more interesting, and the musical examples are a little bit harder to come by. And finally, we're going to get to advanced self-reference. Things like, this sentence is false. And now the loops take on stranger meanings. You get contradictions. Musically, Bach was able to make music with these sorts of loops. Mathematically, these sorts of loops produce really unexpected consequences. And we're going to look at very, very difficult mathematics from as recently as the 1930s. But let's start by looking at self-reference in music. That opening was a little bit strange. Let's skip forward a little bit and see what music has to say about basic self-reference. My friends, composers have manipulated this quirky, at times headache-inducing technique of self-reference in myriad ways. Just to make myself perfectly clear, my main point today is this. Self-reference creates beauty and a bit of strangeness in classical music, which is, of course, more properly called concert music. Let's look at basic self-reference in classical music, which is pieces that reference themselves. Now, basic self-reference in classical music is fairly common. Western composers like to take snippets of earlier parts and play them later to sort of refer you back to keep those things connected in a piece. One of the most popular pieces of all time does this. In fact, Beethoven's Ninth Symphony does this right before it gets to the famous Ode to Joy. So let's examine exactly how he does that. Now, Beethoven's Ninth Symphony was finished in 1824. It was first performed in Vienna with Beethoven sitting right next to the conductor, unable to hear a thing. The last movement, the fourth movement, is the one that contains Schiller's poem An die Freude, or To Joy, hence the name Ode to Joy. Now, after an opening raucous blast, Beethoven intersperses a vigorous cello line with references to earlier movements. The piece is quoting earlier parts of itself. This basic form of self-reference. The symphony is referencing itself. So let's hear these themes from the earlier movements separately, and then as self-reference at the beginning of the last movement. So the theme from the opening movement is marked allegro ma non troppo, fast but not too fast. And it sounds like this. That's sort of the opening motif from that. In the second movement, we have a theme that's much faster. The second movement is marked scherzo, a joke. And it's in a fast 3. And it sounds like this. And then we get to the third movement, adagio molto e cantabile. Very slow, smooth in a singing way. And here's the opening line for the violins, the sort of theme from the third movement. So beautiful. Now let's see how Beethoven references these when we get finally to the fourth movement. Now what you're going to hear, the fourth movement is marked presto, fast. And what you're going to hear is the splashy brass theme, and then you're going to hear alternating the cello themes with quotes from the earlier movements. Now don't worry, we're going to show you on screen which parts are which. So let's listen to the first few minutes of the last movement of the Ninth Symphony of Beethoven. My friends, this is hardly the only example of self-reference in the concert music repertoire. Examples leap from the pages of the scores of Western music. Mahler's First Symphony quickly comes to mind, Der Titan. They're as numerous as overzealous rabbits, reproducing their way into overpopulated oblivion. If we only didn't have to share this stage with math, we could hear more of them. But for now, let's see how mathematicians use self-reference. Mathematicians use basic self-reference all the time. Functions, sequences that refer to themselves. Think about the Fibonacci numbers. Sequence that comes up everywhere. Pine cones, sunflowers, Indian poetry. Remember, it's 1, 1, 2, 3, 5, 8, 13. To get the next, you add the two previous terms. This is a form of self-reference. You see, each term refers back to earlier terms. In math notation, f sub n plus 1 is equal to f sub n plus fn minus 1. There's a name for this sort of self-reference in math and computer science. These are called recursively defined functions. Recursion here is the function f recurring on both sides of this equation. We can look at other examples of mathematical self-reference. If we have a function defined on a small interval, say 0, 1, and we want to repeat it again, we want it to go on and do exactly the same thing, we write f of x plus 1 is equal to f of x. What's f of 2? It refers back to f of 1. f of 2 is f of 1 plus 1, and that should be f of 1 according to our equation. What's f of 1 1/2? That refers back to f of 1/2. f of 1.5 is f of 0.5 plus 1, and so that's the same thing as f of 0.5. You actually get these long chains. You get f of 5 is equal to f of 4 is equal to f of 3 is equal to f of 2 is equal to f of 1. We can look at it graphically. Anytime you have a function defined on 0, 1, we can replicate that between 1 and 2, and we replicate that between 2 and 3, all because of the self-reference contained in this equation, f of x plus 1 is equal to f of x. Now we can also create loops with this, and you probably have seen this if you've taken a computer science class. Now, when I was programming, I was using outmoded languages like Pascal and Fortran, but we used to create loops, and we used to use counters to do things. We would start a loop, and then we would set the counter to be equal to 0, and then we would do some sort of work. And then at the end of the loop, we would say, counter equals counter plus 1. There's the self-reference. And now, unless we're done, we sort of go back to the start of the loop. The self-reference here is that the counter is equal to the counter plus 1. It refers back to itself. It actually refers back to an earlier state within the chain. So I know that self-reference in mathematics gets much more complicated than this, and I'm sure the same is true of self-reference in music. But let's see what self-reference in sort of an intermediate level of complexity looks like in music. For composers, basic self-reference was a piece referencing itself. Intermediate self-reference in music might be a composer referencing him or herself. Now, there are two famous examples of this that we're going to hear about today. One is Johann Sebastian Bach, and the other is Sir Edward Elgar. Let's take the Elgar first. Now, Edward Elgar was a British composer, born in 1857. He was one of the first composers to really embrace recorded music. He recorded orchestral works with the label HMV as early as 1914. One of Elgar's most famous works was probably Pomp and Circumstance. You probably hear this when you go to graduations. You might hear it again and again and again. But he did write many other tunes, including a very famous piece called Enigma Variations. The Enigma Variations were composed in 1899. Now, back in 1898, in that fall, Elgar was finished teaching violin lessons in his house. He lit a cigar and he started just improvising on the piano. In another room, his wife, Alice, said, "I like that tune. Play it again." And Edward played it again, and again, and again. And he started playing it how his friends and family would play it. And that's how we get the name of this piece. You see, Elgar took the original tune to his grave. We don't know what the original tune is. We only now know how Elgar thinks his friends would have played it. That's how we get Enigma Variations. The original tune is still an enigma. One of the more famous is actually variation number 9 called Nimrod, after a friend of his, Augustus Jaeger. We get Nimrod because Jaeger in German means hunter, and Nimrod was Babylonian, the hunter before the Lord. Now let's look at Elgar's self-reference that he uses in this piece. You see, the first variation in this piece is labeled in the score CAE, and that stands for Caroline Alice Edgar. It's the second one where the self-reference comes in. The last segment of this piece is labeled in the score EDU, and that's for Edu or Edward, and that is Edward Elgar himself. This is the self-reference. You see, Sir Edward Elgar composed this little bit of music that we don't know, and this is Sir Edward Elgar himself telling us how Sir Edward Elgar would play this theme that Sir Edward Elgar took to his grave. This is self-reference in music. Let's listen to this, the last movement of the Enigma Variations. That was Elgar's self-reference. To understand Bach's self-reference, we need to know a little bit about music in Germany, and in particular how they notate the names of the notes. Now, we've talked about how we notate names in our system. We have A and C sharp and E flat and things like that. In Northern Europe, including Germany, their B was RB flat. And then to indicate RB, they used the name H. Why was this so important to Bach? Because now, in the German system, B, A, C, H, all four of those are now notes. And so it would sound like this if you played B, A, C, H in the German system. And so Bach, because of this German system, could encode his name in his music. Now he could do this in up an octave, he could do it down an octave like that. He could encode his name in these pieces as much as he wanted. And he actually wrote Bach, this little phrase, this motif, into many different pieces. Let's look at some of those examples. The most famous might be the Art of the Fugue, Die Kunst der Fuge. In Contrapunctus number 14, it is unfinished. His son, C.P.E. Bach, Carl Philipp Emanuel Bach, wrote in the score, Über diese Fuge, wo der Name Bach in Kontrasubjekt angebracht worden, ist der Verfasser gestorben. In this fugue, where the name Bach is written in the countersubject, where it's actually written into the music, the composer died. C.P.E. Bach is telling us that this is the last thing that Bach was writing. Now, it turns out that there's some disagreement whether or not that's actually true, whether or not Bach wrote this and then passed away. There's some indications that C.P.E. Bach might have written that in much later. But it remains that the motif, B-A-C-H, is written into this particular fugue. And so let's listen, and we're going to start exactly where he starts quoting B-A-C-H, Bach. This is where Bach is using self-reference in his own music. Let's listen to that. Let's listen to one more example of Bach self-referencing himself. And this comes from the Brandenburg Concerto No. 2. Interestingly, the Brandenburg Concerto No. 2 is sometimes used as intro music for great courses. Now, near the end of the first movement, the bass line plays B-A-C-H, and it sounds like this. Let's listen to a short clip first where it's just this particular phrase. And here's what it sounds like in the flow of the piece. This is toward the end of the first movement of Bach's Brandenburg Concerto No. 2 of 1721. Listen for Bach referencing himself in the bass line. Other composers actually honored Bach in the same way. Other composers would write B-A-C-H into their music as sort of an homage to Bach. There's actually an entire website devoted to exactly this. Some other composers did more of self-reference, spelling their own names. Now, there are a lot of problems, of course. There are problems that the letters don't always match up with the notes. And so they use tricks of musical nomenclature, sharps, flats, linguistic tricks, puns, in order to do the self-reference. This includes Robert Schumann, Franz Schubert, Johannes Brahms, even Dmitri Shostakovich. Imagine if you're Shostakovich and you're trying to write your own name into your piece, and your name is Dmitri Shostakovich. He actually did this by shortening the German form of his name. You see, in German, Shostakovich is written SCH at the beginning. And so what he would do is he would write in DSCH as a short for Dmitri Shostakovich. Now, where does the S come from, you might ask? S in German notation is R-E flat. And so his name would sound like this. Again, he's using German notation and a bunch of shorthands in order to write himself into his music. He's doing self-reference. Now, I find these musical forms to be fun and intriguing, and I wonder what mathematics looks like as intermediate self-reference. Let's see. Here's a fun mathy version of self-reference that I would probably put at the intermediate level, and it's made the rounds in math circles lately. Multiple choice. If you pick an answer at random from the choices below, the probability that you will be correct is, and now your choices are A, 25%, B, 50%, C, 0%, or D, 25%. You see the self-reference here? The answer is the probability of picking the correct answer. If you're sort of a puzzle person, you might want to take a break for a second and think about this. We're going to analyze the possibilities. Now there are 4 answers, each of which is equally likely, so that's 25% chance of picking each one. But the 25% appears twice. And so if we pick at random, there's a 50% chance of picking the 25%. So maybe the answer should be 50%. But 50% appears only once, and the chance of picking 50% is 25%. So neither 25% nor 50% could be correct, so the right answer should be 0%. But 0% appears once, and there's a 25% chance of picking it. So no answer is the correct percent chance of picking that answer. Now there's a sort of a cheeky way around this. You could write in as option E, 20%, and then that becomes the right answer. Let's look at more mathy examples of self-reference at the intermediate level. In some sense, all differential equations are a form of self-reference. Let me tell you what I mean by that. Let's take the easy differential equation y prime equals 1/2 y. This is among the simplest differential equations you could write. The meaning of this one is that how quickly does y change? That's y prime, the change in y. And the answer to that question is the change is half the size of y. Now, you could use this, and you could use other constants besides 1/2. But this would model something like exponential population growth. Think about starting with 100 rabbits, and maybe at every time step, half of them reproduce. And so you have half of them at the next time step. So you get additional 50 rabbits. But now you have 150 rabbits. So now when half of them reproduce, you get an additional 75 rabbits. That's the exponential growth part. Things keep growing faster and faster. You spiral upward. The key self-reference here is that the function appears on both sides of the equation. It's a function referring back to itself. Back in lecture 1, we were studying a vibrating string. We looked at the wave equation, which is another example of a differential equation. Actually, it's a partial differential equation. And the wave equation looked like this. Remember that u of x and t represented how far above the median line our string went at position x and time t. Notice that it occurs on both sides of the equation. It's a form of self-reference. U is related to itself in this particular way. Every differential equation, and in fact every partial differential equation, is some form of mathematical self-reference. But we can also look at geometrical examples. Let's look back to the golden ratio, which we talked about in lecture 5. Remember, we looked at its continued fractions with all ones. Remember that the golden ratio here is like pi. It's a number with special properties, and it's also irrational. You can't write it as a fraction. Now the golden ratio, we normally think of the golden ratio not in terms of the continued fraction, but in terms of it being 1 plus root 5 over 2, the ratio of the sides of phi. The main property geometrically of the golden ratio is that if you take a rectangle whose sides are exactly in that ratio and remove a square, the largest square you can, the remaining rectangle has the same proportions as the original. And then from that you can remove the largest square, and the remaining rectangle has the same proportions as the original. And you can do that again and again and again. In fact, if you inscribe a curve inside each one of these squares, roughly a quarter circle in each square, you get this beautiful curve. And it's actually called a logarithmic curve. And when we look at that, it's this sort of spiral, and it's just one example of a logarithmic spiral. And there are others depending on the size, but this is the one related to the golden ratio. Now, we've seen that it's 1 plus root 5 over 2, but we've also seen that it's this continued fraction with all ones. Now, an interesting mathematical question, if you're being skeptical, you should be asking, how do we know those two are the same? And in order to see that, it takes some algebra and a little bit of self-reference. So let's look at the continued fraction with all ones. And let's call that value x. Now the denominator, when we look at the denominator in that expression, it's just another copy of x, right? It's just 1 plus a fraction with an infinite sequence of further fractions all involving ones. That's what x is. That means that the whole expression x is actually equal to 1 plus 1 divided by x, the entire expression again. We write out this equation in algebra, and it's just that x is equal to 1 plus 1 over x. And here's the self-reference, because x appears on both sides of this equation. When we solve this, we just multiply both sides by x. We get x squared is equal to x plus 1. We can subtract x plus 1 from both sides, giving us this quadratic equation. Remember, to solve a quadratic equation, there's a formula, coincidentally enough, called the quadratic formula. When we apply that formula, we might remember this from high school, negative b plus or minus the square root of b squared minus 4ac all over 2a. We apply that in this particular case, and we get phi. We get 1 plus root 5 over 2. We actually get 1 plus or minus root 5 over 2. We know it can't be the minus sign because that value would be less than 1/2, and our number is clearly bigger than 1. Let's look at a geometrical version of self-reference, the Möbius strip. It's probably the easiest geometrical version of self-reference we can come up with. We take this long strip of paper, and it appears to have two sides or faces, a front and a back, and we can fix that with a little bit of self-reference. We twist once and tape the ends together, and now the front side continues on to what was the back side, which continues all the way around back to the front side. It's the Möbius strip. If you think about it, it has just one face and one edge. How weird is this Möbius strip? To show you the strangeness of self-reference, I'll do two demonstrations with this strip. First, I'm going to cut it down the middle. I'm going to cut it exactly in half, down the middle the long way. And if you're intrigued about this, you should guess what's going to happen when I do this. When I cut it down the middle, I keep cutting all the way around, and amazingly, I end up with a single piece of paper. And now it actually has two faces and two edges. Another thing I can do with this Möbius strip, instead of cutting it in half, I can cut it in thirds. And when I cut it in thirds, now again, you might want to think about this and pause for a second, but when I cut it in thirds, one of the surprising things you'll notice is that I don't have to start my cut over. It's actually one very long cut. And when I do this, the result is fairly surprising. I get two separate loops, but they're interlocked. There's the shorter one, which is a thinner version of the Möbius strip. And then there's the longer one, which is a version of what we had when we cut it exactly in half, except now that's thinner. The properties of the Möbius strip are very strange indeed. There are other topological beasts that have similarly strange properties, and like most of the self-reference you see, it's a little bit above the basic level, I'd say. Well, that I think is intermediate self-reference in mathematics. Let's see what our musical friend can show us about intermediate self-reference in music. My friends, I fear that musical examples of advanced self-reference are nearly as rare as pigs actually taking flight. There are only a few, precious few, examples of self-reference, ingenious enough to earn the label of advanced. One is definitely a crab canon. Now this is a masterpiece of musical form and contrapuntal complexity. It's a duet formed by playing a piece of music forwards and backwards simultaneously. Let's look at a crab canon of Bach. In 1746, Bach was challenged by Frederick the Great of Prussia. Compose a canon based on a theme of his choosing, and he chose a very odd little theme. I'll play it for you on violin. Here's the theme that the King of Prussia gave to Bach to compose a fugue on. That's a very little odd theme indeed. Now, on the spot, Bach was able to improvise a 3-part fugue based on that theme, but he apologized that he couldn't do better, and when he returned to Leipzig from Potsdam, he wrote a 6-part fugue based on this same theme. And this is known as a musical offering. One of the parts of the musical offering is a crab canon, so let's look at that. The crab canon, when you write it out, has 2 parts, but if you notice, the second part is the same as the first, played in reverse. In the language of transformations, the second part is simply the retrograde of the first part. Now this hauntingly beautiful melody, based on a theme not of his own choosing, magically fits with its own retrograde to form a duet. Let's listen to this crab canon. In Bach's crab canon, the second part reads the music retrograde, or from the end to the beginning. In a table canon, the second part plays retrograde inversion, from the end to the beginning, but inverted, upside down. My friends, you may have seen this type of canon demonstrated in an earlier lecture in this math and music course that you're currently watching. I certainly don't want to replay that piece. It simply cannot be correctly attributed to Mozart, though. But let's look at this again. Let's look at the table canon. Now, a table is such a boring piece of furniture to use. Let's find a more interesting way to represent this piece. So, suppose we were to write out the table canon on one long staff. Now, it would be much too small for you to read, but you can imagine it written out here. And it would start here at the beginning, and you would be able to go through, you would play through the middle, and then you would get here to the end. And then player 2 would be playing from the end, but upside down, through the middle, and finally to the beginning. Now, it's a little hard to read music upside down, so let's see if we can give these guys a little bit of help. I'm going to rip this exactly in the middle. You notice that middle here is split. And I'm going to flip them over and tape them together with a twist. And when I do that, let's see what it looks like. Here I'm taping together, and then you see here's the end of the word middle, and here's the beginning of the word middle, and they need to be flipped in order to tape together. So let's do exactly that. Now I'm going to tape just to make sure it stays together. And now, let's think about what the players are supposed to do. See, player 1 is supposed to play starting here at the beginning. Keep going. There's the middle. Play through the middle, right here, and finally get to the end. Player 2, on the other hand, is supposed to play starting at the end and upside down, and here we go. They're supposed to keep playing, keep playing. Notice that they get to the middle now, upside down. And they keep playing, and they keep playing. And finally, they get to the beginning, upside down. Now, amazingly, if both players wanted to keep going, if they wanted to repeat this, they could just keep going. The second player would just start again at the end, upside down. On this confounded strip, it sort of works out nicely. I'm sure mathematicians have some name for it. The piece would just keep repeating musically. A mathematician might say that this is sort of infinitely long in some way. Canons such as these, and those you heard about in earlier lectures, they represent the pinnacle of self-reference in music. There simply is nothing better. Let's see what the ultimate in self-reference looks like in the mathematics world. Finally, we've come to the Gödel and Gödel, Escher, Bach for advanced self-reference in mathematics. First, we have to understand the context in which Gödel was doing his work. In 1910, Alfred North Whitehead and Bertrand Russell published Principia Mathematica. Their goal was to provide axioms that would give a stable base for mathematics, sort of the same way Euclid did for geometry, except they were trying to do this for arithmetic and all of the theorems that come with arithmetic. Now, Whitehead and Russell, along with David Hilbert, sought axioms that were first consistent so that you couldn't prove both a statement and its opposite. That would be a problem. And second, complete. Axioms that proved all the true statements. If a statement was true in their system, they wanted to make sure that they could prove it just using the axioms that they provided. This is sort of a particular view of mathematics, that with the right axioms, there might be two kinds of statements in the world. There would only be true statements, all of which would be provable, and then there would be false statements, none of which would be provable. Gödel's work ruined their dreams. Before we can talk about Gödel's work, let's back up a little bit to the liar's paradox. Now this is, again, sort of a tricky version of self-reference. Consider the statement S. This statement is false. Now let's think. Is S a true statement? Well, no, because if it's true, then the statement says that it's false, and that's not possible. Is S a false statement? Well, if S is a false statement, then this statement is false, so the statement has to be true. So S can be neither true nor false. Gödel used this kind of self-reference to burst the bubble of Whitehead and Russell's goal, their dream. You see, if you had a set of axioms strong enough to prove basic arithmetic truths about the natural numbers, then Gödel gave sort of a recipe, a way of producing within your system the statement G, this statement is not provable. Let's think about why that works. G, this statement is not provable. Is G itself provable? Well, it can't be provable because then the statement would be both provable and not provable, and we would have inconsistencies. And so G is true exactly because it's not provable. So the world is not quite as black and white, sort of true and provable versus false and unprovable. Gödel managed to find within the true statements something that was necessarily not provable. Kurt Gödel put this in his 1931 masterpiece, On Formally Undecidable Propositions in Principia Mathematica and Related Systems, Part 1. And in this, he destroyed the dreams of Whitehead, Russell, Hilbert, and many other mathematicians. Now, this first theorem says that no theory strong enough to do arithmetic is complete. There are true but unprovable statements. His second theorem actually says something different. It says that no theory strong enough to do arithmetic can prove its own consistency. Remember, consistency is that you can't prove both S and not S. A system might be consistent, but you can't prove within the system that it is consistent. Now, I would really love to walk you through the details of Gödel's work. This work is incredibly difficult, and when I was an undergraduate, I did an entire semester's independent study with Professor Bird just on the incompleteness theorem, an entire semester to prove the incompleteness theorem. The core ideas here involve coding statements about mathematics with numbers so that you can talk about those statements within the mathematical language. The key to all of this is actually unique prime factorization, that every natural number can be written as the product of primes in exactly one way. Really, I think this is the height of mathematical self-reference. This is a self-referential statement that shows the futility of axiomatic systems for arithmetic. Mathematicians since Gödel have had to deal with this fact, and it's spurred surprising new areas of research. Anyway, what Gödel does is create a sentence that talks all about itself. It's sort of like this entire lecture. I hope you've enjoyed our tour through the strange worlds of self-reference in both mathematics and in music. Now, next time, we're going to move away from these implicit connections between the two subjects of math and music, and we're going to see how composers explicitly used mathematics in composing their works. Thanks for joining us.
That's a wrap. Good job, Dave.
Thanks, Zach.